Deep in the cosmic microwave background, a vast, cold anomaly chills the universe. This cold spot defies our understanding of cosmic structure, a baffling void where there should be warmth. What created this cosmic mystery, and what does it tell us about the universe's earliest moments? Join us as we explore the enigma of the cold spot and the profound implications it holds for cosmology. The cold spot anomaly. The cold spot anomaly presents a significant enigma in our understanding of the cosmos. This region of the cosmic microwave background, CMB, radiation is notably cooler than the surrounding areas, a discrepancy that challenges standard cosmological models. Initial observations suggested it might be an artifact or a statistical fluke, but further data have solidified its existence, prompting deeper investigation into its origins. The sheer scale of this cold region, spanning billions of light years, makes it difficult to explain through conventional astrophysical phenomena alone. Its existence implies that something unusual is present in the universe, or that our current theories require revision. One leading hypothesis suggests the cold spot could be the result of a supervoid, an immense, underdense region of space. If a vast number of galaxies and matter are absent in this area, the gravitational pull on the CMB photons passing through would be less than average. According to the integrated Sachs-Wolf effect, photons gain or lose energy as they traverse gravitational potentials. If CMB photons travel through a vast supervoid, they would expend less energy climbing out of gravitational wells than they gained falling in, resulting in a cooler observed temperature. However, the predicted temperature drop from a supervoid of typical size and density deficit doesn't fully account for the observed coldness of the anomaly, suggesting it might be an exceptionally large or unusually empty void. Another, more speculative, explanation involves the possibility of interactions with other universes. This concept, rooted in certain string theory and multiverse models, posits that our universe might have brushed against another, a cosmic collision of sorts. Such an event could have imprinted a bruise on the CMB, manifesting as the cold spot. While highly theoretical, this idea offers a potential explanation for the anomaly's profound coldness and its seemingly unusual characteristics that are difficult to reconcile with standard physics. The implications of such an interaction would be revolutionary, fundamentally altering our perception of reality and our place within a potentially larger cosmic structure. Regardless of its ultimate cause, the cold spot anomaly serves as a crucial testbed for cosmological theories. It pushes the boundaries of our knowledge, encouraging scientists to explore exotic phenomena and refine existing models. Whether it points to an extraordinary void, a novel physical process, or even evidence of a multiverse, the ongoing study of this cosmic oddity promises to yield significant insights into the fundamental nature of the universe. Its persistent mystery underscores how much we still have to learn about the vast expanse beyond our own cosmic neighborhood. Cosmic microwave background radiation. The cosmic microwave background radiation, often abbreviated as CMB, represents the afterglow of the Big Bang, a faint, pervasive light filling the entire universe. It is essentially a snapshot of the cosmos when it was only about 380 years old, a time when the universe had cooled sufficiently for neutral atoms to form, allowing photons to travel freely for the first time. This ancient light, stretched by the expansion of the universe over billions of years, now arrives as microwave radiation, a crucial piece of evidence supporting the Big Bang theory. Its discovery in 1964 by Arno Penzias and Robert Wilson was serendipitous, initially mistaken for unwanted noise in their radio antenna. Studying the CMB reveals intricate patterns and temperature fluctuations across the sky. These tiny variations, on the order of parts per 100,000, are not random noise, but represent the primordial seeds of all structure we see today, from galaxies to galaxy clusters. Slightly hotter or colder regions in the CMB map correspond to areas of slightly higher or lower density in the early universe. Over eons, gravity amplified these initial density differences, drawing matter together to form the cosmic web of stars and galaxies. Satellites like COBE, WMAP, and Planck have provided increasingly detailed maps of these anisotropies, allowing cosmologists to precisely measure fundamental parameters of the universe. One particularly intriguing anomaly observed in the CMB data is the cold spot. This vast region of the sky exhibits a temperature significantly lower than the surrounding CMB. While the overall CMB temperature averages around 2.7 Kelvin, 270.45 degrees Celsius, the cold spot is several millikelvins cooler. Its existence presents a puzzle for standard cosmological models. Various explanations have been proposed, ranging from statistical fluctuations in the early universe to more exotic theories. Some theories suggest the cold spot could be the result of a supervoid, an enormous region of space with a much lower than average density of galaxies. If such a void existed between us and the CMB-emitting surface, the photons passing through it would lose energy due to the gravitational pull of the matter in the void, appearing cooler to us. Another, more speculative, hypothesis involves the possibility of colliding bubble universes or exotic topological defects from the very early universe. However, the statistical likelihood of such a large anomaly occurring within the standard lambda-CDM model is still under intense investigation, making the cold spot a fascinating frontier in our quest to understand the universe's origins and evolution. Possible explanations for the cold spot. One hypothesis suggests the cold spot might be a supervoid, an unusually vast region of space containing far fewer galaxies than expected. These cosmic underdensities are predicted by some cosmological models, and while most are relatively small, the cold spot could represent an exceptionally large one. If it is a supervoid, the cosmic microwave background radiation passing through it would be slightly cooler due to the gravitational influence of the surrounding matter. The shear scale required for such a void to produce the observed temperature anomaly presents a significant challenge to this explanation, as it would be one of the largest structures ever detected. Another intriguing possibility involves colliding bubble universes. According to some theories of eternal inflation, our universe might be just one bubble among many, constantly budding off from a larger, inflating multiverse. If two such bubbles collided in the early universe, the impact could have created a region with different physical properties, potentially leading to the observed coldness. This scenario, while highly speculative, offers a unique explanation rooted in advanced theoretical physics. The energy released during such a collision could have left an imprint on the fabric of spacetime, manifesting as the cold spot. A more conventional, though still debated, explanation involves an unusual distribution of matter, specifically a large cluster of galaxies or a supercluster that is not easily detectable. While the cold spot appears as a region of lower temperature in the CMB, this could be an artifact of the integrated Sachs-Wolf effect. This effect occurs when CMB photons pass through large-scale structures, gaining or losing energy, depending on whether they are climbing out of or falling into a gravitational potential well. A particularly massive and elongated structure, perhaps one lying at a specific angle relative to our line of sight, could potentially cause this cooling effect without being easily visible through other means. However, extensive surveys have yet to find a structure of sufficient size and mass to definitively account for the anomaly. Supervoid hypothesis. The supervoid hypothesis proposes that the cold spot, a region of unusually cool temperature in the cosmic microwave background, CMB, radiation, is not caused by a statistical anomaly, but by the presence of an immense, underdense region of matter, a supervoid, located between us and the CMB's origin. This supervoid would be so vast that it would significantly affect the passage of photons from the early universe. As photons from the CMB travel through this region, they would lose energy due to gravitational redshift, a phenomenon where light traveling out of a gravitational potential well loses energy. This energy loss would manifest as a lower temperature observed in that specific direction on Earth. If this hypothesis is correct, the supervoid would be an extraordinary structure, far larger than typical voids found in the cosmic web. These voids are already enormous, vast expanses of space containing very few galaxies. However, a supervoid capable of producing the observed temperature anomaly in the CMB would need to be on an unprecedented scale, stretching for potentially billions of light years. The existence of such a colossal structure would challenge our current understanding of large-scale structure formation in the universe, suggesting that matter distribution could be even more heterogeneous than previously modeled. Evidence supporting the supervoid hypothesis comes from observations that have detected a significant void in the direction of the CMB cold spot. This void, known as the Eridanus supervoid, appears to be a vast, relatively empty region of space. While the supervoid itself doesn't emit radiation, its gravitational influence on the CMB photons passing through it is the key prediction. Analyzing the distribution of galaxies and matter in this region helps astronomers map the extent and density of this potential supervoid, providing crucial data to test the hypothesis. However, the supervoid hypothesis is not without its challenges and alternative explanations. Some cosmologists suggest that the cold spot could be a result of statistical fluctuations, a rare but not impossible outcome in the random distribution of temperatures in the CMB. Other theories propose exotic physics, such as the presence of cosmic strings or other topological defects from the early universe, which could also imprint cold spots on the CMB. The ongoing debate highlights the complexity of interpreting CMB data and the continuous effort to refine our cosmological models. Exotic physics theories. The cold spot, a peculiar anomaly in the cosmic microwave background, CMB, radiation, has sparked numerous discussions and investigations into exotic physics theories. One prominent hypothesis suggests that the cold spot might be evidence of a supervoid, a vast, underdense region of space far larger than typical voids. If such a supervoid exists, its gravitational influence on the CMB photons passing through it could create the observed temperature BOSS. However, the sheer scale required for such a supervoid pushes the boundaries of our current understanding of large-scale structure formation within the standard cosmological model. Another intriguing possibility involves theories beyond the standard model of particle physics. Some researchers propose that the cold spot could be a bruise left by a collision with another universe. This multiverse hypothesis, while highly speculative, posits that our universe might be one of many, and interactions between them could leave detectable imprints on the CMB. Such an event would require a radical rethinking of cosmic origins and the nature of reality itself. Furthermore, the cold spot has been linked to theories involving exotic dark matter or dark energy interactions. Perhaps a non-standard form of dark matter or an unusual behavior of dark energy could create localized regions of lower energy density that manifest as the observed cold region. These theories often involve modifications to Einstein's theory of general relativity or introduce new fundamental forces and particles that are not yet experimentally confirmed. The ongoing quest to explain the cold spot continues to drive theoretical innovation, pushing physicists to explore the very limits of what we know about the cosmos. Observational evidence and challenges. The existence of the cold spot, a region of the cosmic microwave background, CMB, exhibiting unusually low temperatures, presents significant observational hurdles. Initial detection was made using the Wilkinson Microwave Anisotropy Probe, WMAP, satellite, which provided the first detailed map of the CMB. Subsequent observations by the Planck satellite, with its higher resolution and sensitivity, confirmed the cold spot's presence and allowed for more precise measurements of its properties. However, the sheer scale of the cold spot, spanning billions of light years, makes it a challenging object to study. Its vastness means that observing it requires synthesizing data from across enormous cosmic distances, a process fraught with potential sources of error. One of the primary challenges in verifying the cold spot's nature lies in distinguishing its low temperature from other astrophysical phenomena. For instance, foreground emissions from our own galaxy, such as dust and synchrotron radiation, can mimic or mask CMB signals. Careful data analysis and sophisticated subtraction techniques are employed to mitigate these foreground effects. Furthermore, the statistical significance of the cold spot's temperature anomaly is a subject of ongoing debate. While it appears statistically unlikely to have arisen from random fluctuations in the early universe, the precise probability is difficult to ascertain due to uncertainties in cosmological models and the limited number of such large-scale structures available for comparison. Another observational difficulty stems from the limited resolution of CMB telescopes. Even with advanced instruments like Planck, the cold spot's angular size on the sky is so large that it is difficult to resolve fine details within it. This limits the ability to probe its internal structure and compare it with theoretical predictions for various exotic explanations. For example, if the cold spot were caused by a supervoid, one would expect to see subtle variations in the CMB temperature across its expanse related to the gravitational effects of the matter deficit. However, current observational data does not provide sufficient resolution to definitively confirm or refute such predictions. The ongoing quest to understand the cold spot thus relies on improving observational techniques, developing more refined data analysis methods, and potentially discovering similar anomalies in other parts of the sky. Implications for cosmology. The cold spot, a region of unusually low temperature in the cosmic microwave background, CMB, radiation, presents a significant puzzle for standard cosmological models. Its existence challenges our understanding of the universe's early moments and the distribution of matter within it. One prominent implication arises from the fact that the cold spot appears to be larger and colder than predicted by the lambda-CDM model, the prevailing framework for cosmology. This discrepancy suggests that either our understanding of the early universe's physics is incomplete, or there are unknown factors influencing the CMB. Several theoretical explanations have been proposed to account for the cold spot's anomalous temperature. One idea is that it could be a supervoid, an exceptionally large region of space with a lower-than-average density of galaxies. Such a void, if it existed during the era when the CMB was formed, could have caused the light passing through it to lose energy, thus appearing colder to us. However, observations have not yet conclusively confirmed the presence of a supervoid of the required magnitude directly linked to the cold spot. Another, more exotic, hypothesis involves the interaction of the early universe with other universes, a concept stemming from multiverse theories. If our universe collided with or interacted with a bubble from another universe, it could have left an imprint on the CMB, potentially creating a cold spot. The implications extend to fundamental physics. If the cold spot cannot be explained by known astrophysical phenomena or standard cosmological parameters, it might necessitate new physics beyond the standard model. This could involve modifications to gravity, the nature of dark matter or dark energy, or even entirely new fundamental forces. The statistical significance of the cold spot, while debated, is high enough that dismissing it as a random fluctuation becomes increasingly difficult. Its persistent presence in observational data fuels ongoing research and debate among cosmologists, pushing the boundaries of theoretical exploration. Further investigation into the cold spot is crucial for refining our cosmological models. Detailed mapping of the CMB and surrounding large-scale structures is essential to either confirm or refute the proposed explanations. If the cold spot is indeed a signature of new physics, its study could provide the first observational evidence for phenomena such as extra dimensions, cosmic strings, or interactions with other universes. This makes the cold spot not just a curious anomaly, but a potential gateway to a deeper understanding of the cosmos and its ultimate origins. So, the cold spot remains one of the universe's most intriguing puzzles. Is it a colossal void, a remnant of a collision with another universe, or something else entirely? Its true nature is still debated, a tantalizing mystery in the cosmic microwave background. What other strange phenomena lie hidden in the vastness of space? Join us next time as we explore the bizarre world of fast radio bursts, mysterious, powerful signals from distant galaxies that challenge our understanding of cosmic events. Subscribe so you don't miss it.